Welcome to Advanced Quantum Chemistry and my 9th lecture on Hartree-Fock theory. The topic of this lecture is the restricted closed-shell Hartree-Fock equations. Now, so far we have written all the Hartree-Fock equations up with spin orbitals, which of course is a natural way to do because the Slater determinant is made from spin orbitals. And the spin orbitals are in general a product of a spatial orbital, phi, and a spin function. And it can be either the spin function alpha or it can be the spin function beta, where alpha is an abstract function which is the spin function for the ms value plus 1/2, and beta is the spin function for the ms value of the electron minus 1/2. Now, there are two ways now how one can make spin orbitals. One can make spin orbitals in this form of what is called restricted set of spin orbitals, where one uses the same spatial orbital for both the alpha spin and the beta spin orbital. And then there's another set of spin orbitals which is called unrestricted, where the spatial orbital for the alpha and beta version of the spin orbital can vary. In this course, we are only going to talk about restricted spin orbitals. The unrestricted spin orbitals and unrestricted Hartree-Fock, you will have to come to our master course on computational chemistry. Now, with this restricted spin orbitals, in order to save a bit space on writing later on the equation, this product of a spatial orbital phi j with the alpha spin function, I want to write shorter, just of writing phi j with a plus, where the plus should remind you of that it's plus 1/2, which is the ms value, and with the beta spin is minus to remind you of that it's minus 1/2. Now, the Hartree-Fock wave function using this restricted set of spin orbitals, we can then write here, where if we had original n spin orbitals, and let's assume right now that we have an even number of electrons, so n is an even number, and then we will have a Slater determinant which is made from n½ spatial orbitals, but they come always twice, one with the alpha spin and one with the beta spin. Now what you want to do now is we want to transform or convert all the Hartree-Fock equations which were originally written in spin orbitals to equations which are written in terms of these doubly occupied spatial orbitals. And the way to do that is we have to integrate over the spin functions. So the spin orbital psi in the Hartree-Fock equations can either be a spin orbital with alpha or beta spin, but the result is actually the same. So let's just derive the Hartree-Fock equations assuming that the spin orbital in the Hartree-Fock equation was an alpha spin orbital. So instead of the spin orbital psi, I have now a spatial orbital phi multiplied with an alpha spin function on both sides. And in order to get rid of the spin functions now, I multiply from the left with alpha spin complex conjugate and I integrate. So I get an integral here on the left side of the Hartree-Fock equation and I get an integral on the right side of the Hartree-Fock equation. Now let's look at the right side first, because here I have the orbital energy, which is a constant. Then I have one spatial orbital, and I have my to a spin function and integrate over the spin of electron 1. Now the orbital energy of course is constant, which I can take out. The spatial function here also does not depend on the spin integration, so I also can take it out. So I end up with having on the right hand side the orbital energy, the spatial orbital, multiplied with an overlap integral of the alpha spin function. And it's actually not the overlap, but it's the normalization integral, and spin functions are normalized, so this integral is just 1, so the spin integration just gives 1 on the right hand side, and we end up just with the orbital energy multiplied spatial orbital. Now on the left hand side we have this integral here, we can again take the spatial orbital out of the integral, because we integrate over spin, and the spatial orbital obviously does not depend on spin. So I get here this integral over the Fock operator, which depends on spin still, because the Fock operator includes spin orbitals, so that depends on spin, multiplied on here the spatial orbital. And this integral here over the Fock operator expressed with spin orbitals multiplied with the spin function, that is our closed shell Fock operator, or is going to be our closed shell Fock operator. And in the following we are going to look at how this looks like exactly. So with this definition here of the closed shell Fock operator, the left hand side of our Hartree-Fock equations now looks like as here have the closed shell Fock operator acting on our spatial orbital. And on the next slides we are now going to look how this closed shell Fock operator turns out to look like. Okay, so we have the closed shell Fock operator acting on spatial orbital phi I now. And here I've written it out again, how we had defined it on the last slide. So here's the Fock operator in terms of spin orbitals, and that consists of course of the core Hamiltonian, but the core Hamiltonian depends only on the position of the electrons. And therefore we can take this operator out of this integral, because that's an integral over the spin of electron 1, and the core Hamiltonian only depends on the position, so we can take it out. And then we get here just an overlap integral of spin orbital alpha with alpha, and they are normalized, so this one is 1. So the only thing which survives from this integral here is here the core Hamiltonian. Now the next term is then the Coulomb operator. And the Coulomb operator consists of an integral over position and spin of electron 2, and the spin orbitals for electron 2, psi j of electron 2, psi j of electron 2, divided by the internuclear distance between the two electrons. And this operator is then acting on, because here it's acting on the spatial orbital phi I. For the exchange integral, which we have here, the situation is a bit more difficult, because of the exchange. So now in the integral over electron 2, we don't have psi j any longer, because psi j is now for electron 1, so we get here psi j of electron 1 here. Whereas here in the integral over electron 2, now we get phi I of electron 2 times alpha of electron 2, because in the Coulomb integral we had phi I of electron 1 times alpha of electron 1, and in the exchange integral electron 1 and electron 2 interchanged in the ket part, so we get now phi I of electron 2 alpha of electron 2. Now these summations here over occupied spin orbitals psi j, they are still over spin orbitals, and since we use doubly occupied restricted orbitals, now this summation over spin orbitals we can split up in one half of the spin orbitals will have alpha spin, and the other half of the spin orbitals will have beta spin. So instead of a summation over n spin orbitals here, we will get summation over n half spatial orbitals with alpha spin and spatial orbital with beta spin. Which means from the Coulomb exchange part, we will get in total now 4 terms. And they are here. This is the core Hamiltonian part, which we already have, and those two are now come from the Coulomb integrals, and those two come from the exchange integrals. So let's look at the Coulomb integrals first. What I have to do now is I replace the spin orbitals psi j with spatial orbitals phi j, and in the first part phi j times alpha, so the electron 2 had alpha spin, so I get phi j alpha of electron 2, phi j alpha of electron 2, and in the second term here I have now over a spin orbitals which had beta spin, so I get phi j with beta spin, phi j with beta spin. And I have to do now the same with the exchange integrals, but I have to be careful now with the exchange. So again here I have psi j, which has now alpha spin. So here I had psi j of electron 2, which becomes now phi j of electron 2 with alpha spin. And I had psi j out here, psi j of electron 1. So this becomes now phi j of electron 1, and again with alpha spin. And in the second one, I have now the summation over j where it's beta spin, so I get phi j with beta spin for electron 2 here. And out there I had psi j, which becomes now phi j with beta spin. Okay, now I can integrate over spin, and I can sort of integrate over spin A or with electron 1 and the spin of electron 2. And if you look at the first integral, there I have electron 1 has alpha spin here and has alpha spin there. And none of the functions, apart from the spin functions or the operator, depend on spin, so I can just make the spin integration. So I integrate over spin of electron 1 with alpha and alpha. That gives me, of course, 1. And the same, you have the integration over spin d omega 2 here with f electron 2, and again I have alpha with alpha, and that's again 1. Now in the second one for electron 1, for the spin of electron 1, I have alpha here and alpha there, and I integrate over that, it gives me 1. And for electron 2, now I have beta spin, but I have beta spin here, complex conjugate, and beta spin there. So if I integrate over the beta spin, that gives me again 1. The third integral is again the same story. I have alpha spin for electron 1. And I also have alpha spin for electron 1 here, and I integrate over that, that gives me 1. And I have alpha spin for electron 2 here and here, so if I integrate that, I get also 1. So in those three integrals, the spin just integrates out to 1. Now let's look at the final one. Here I have alpha complex conjugate for electron 1. And let's see where is the spin of electron 1 again. That is here. But this is now beta spin. So I actually get an overlap integral of alpha spin for electron 1 with beta spin for electron 1. But the spin functions are orthonormal, which means they are orthogonal. So this integral is actually 0. And for electron 2, I actually get the same situation. Here I have beta spin for electron 2, complex conjugate. And where I have electron 2 again, I have it here. And again, here I have alpha spin, so I get this integral. Also for electron 2, I get one where I have beta with alpha spin, but they are orthogonal. So those two spin integration gives 0, which means because of the spin integration, this second exchange integral disappears. So I end up with having two Coulomb integrals, this one, and I have one exchange integral only because of the spin integration. So if I collect them now, again, the spin is now gone. I just have a Coulomb integral here, or a Coulomb operator integral over spatial function. I had two of them, whereas I only have one of the exchange integrals. And now I can define my closed shell Coulomb and exchange operators. So again, this, like for the spin case, this is now my Coulomb operator. It's a closed shell Coulomb operator, not only closed shell, but it's also in spatial function now, and therefore I've removed the prime there. So that's the Coulomb operator expressed in a Coulomb operator for spatial orbitals. And again, I can't write the exchange operator as just an operator. I only can write the exchange operator up if it's acting on a function, and now it's an exchange operator in terms of spatial function, and it's acting on a spatial function. So this is the action of the spatial closed shell exchange operator. And at the end then I get a closed shell Fock operator in terms of spatial orbitals, which looks like this. and which distinguishes itself from the spin orbital case, because I have, first I have a sum over spatial orbitals here, which is because I have double occupied spatial orbitals. I only have half as many spatial orbitals as I had spin orbitals originally, because they're double occupied, but I get twice the Coulomb operator contribution, only once the exchange operator contribution because of the exchange of the spin functions. Now finally, here I have all the closed shell equations for Hartree-Fock. So I get the closed shell Hartree-Fock equation, closed shell and with spatial orbitals here. So this is a spatial orbital. Then we can also write up an expression for the Hartree-Fock energy in terms of doubly occupied closed shell spatial orbitals. So all these summations here are over the number of spatial orbitals, which is half as large as the number of spin orbitals, and therefore I get a 2 here. So I have the contribution from the core Hamiltonian, and I have here twice 2 Coulomb integrals, but only 1 exchange integral. And here I've implicitly defined a sort of a Coulomb integral as being Jij, and here's the exchange integral. So this is the Coulomb integral, and this is an exchange integral. And similarly, I can write up an expression for the orbital energies, which is now the energy of a spatial orbital phi I, where here I have the integral over the core Hamiltonian, and I get again 2 Coulomb integrals and 1 exchange integral. And the final equation here is again using this shorthand notation for the Coulomb integrals and the exchange integrals.